Good morning. Uh, in yesterday's class, we have covered field headings. Now today, let us go to new heading. That is color of complexes. Color of now. See here, I am with a few substances in my hand. The cap of this pen is showing blue color. The cap of this is showing red color, and my shirt is white in nature. Now, why different chemicals are showing different colors? What is the reason behind it? Let us see this today. Now, if I say about the D block, most of the chemicals belonging to this D block, in particular 3D series, all are almost colored in nature. Right? Almost all are colored in nature, either in their neutral state or in any one of their common oxidation state. Here we are with one tabular column. Let's go through it once. Configuration, example, and color. 3D0, 3D0, 3D1, 3D2, 3D3, 3D3, 3D4. My example is scandium in +3 state, titanium in +4 state, titanium in +3 state, vanadium in +4 state. Something missed. 3D0 scandium, 3D0 titanium, 3D1 titanium plus this again. Vanadium plus 3. Color of this chemical is colorless, same, then comes purple, blue, green, violet, violet. Right. Now here we have a few more examples. Configuration is 3D4. Example is chromium +2 oxidation state, and the color is blue. 3D5 configuration, manganese with +2 oxidation state, color is pink. Fe +3, yellow. 3D8 nickel in +2 state, green. 3D9 copper in +2 state, blue. 3D10 zinc in +2 state, colorless. Okay. See friends, as I said, different components, different chemicals are with different colors. Like my shirt is colorless, this is blue in color, that pen was red in color. In the same way, this D series, the elements present in the D block shows different colors, either in their neutral state or in any one of their common oxidation state, as I said previously. Now, see here, scandium in +3 state is with configuration 3D0, which is colorless in nature. Titanium in +4 state with 0 configuration, means 0 electrons next to d orbital, it is showing colorless. means it is not having any color. Zinc in +2 state is with 3D10 configuration even when it is colorless. Now, except this, when I go to all other elements present here, right, are showing different color in different oxidation state. Once you have a look over titanium. Titanium in +3 state with one electron in the d orbital is showing purple color. And in +4 state it is colorless. Vanadium in +4 state is showing blue color. Vanadium in +3 state is showing green, and in +2 state it is showing violet color. In the same way, we are having few more examples here at the right of the board. Now, the question comes, why the chemicals are showing color? What is the reason behind it? See, when a given chemical, let us consider this pen itself. When a given chemical absorbs visible light, when a visible light falls on it, this chemical absorbs some frequency range from this visible light and it transmits its complementary color. And that transmitted complementary color can be seen by our naked eyes. Means it absorbs some wavelength and emits some other wavelength. That emitted light is identified by our eyes, and we say that this chemical looks like blue. It is blue in nature because this is the transmitted light. Absorbed light is something else, and this is the transmitted light. In the same way, all these things. Now, let us see. Before that, let's see one diagram and then we'll come to this point what I wanted to tell you just now. Right? And with one diagram here. Let us consider. And with one substance. I don't know what substance it is. In general, I am considering one substance. Right? On this, some light has fallen. Then some light is emitted. This emitted light is seen by us. Now consider this substance is absorbing red light. Let us consider when this substance absorbs red light, then the observed, the transmitted, the complementary color will be exactly opposite to that. Once you have a look on this diagram, opposite to red is green, right? So the color of this substance will be green in nature. Now let us consider this substance, instead of absorbing red color, it has absorbed yellow color. Let us consider. If it is absorbing yellow, then its complementary color will be violet. Means it will be violet in nature. So with the help of this diagram, we can predict directly which chemical shows what color when it absorbs some particular color. Now, you may get a doubt, sir, if XYZ substance is given to us, right? Here, with the help of diagram, you are considering in general this chemical is absorbing violet, yellow color, so it emits violet color. It look violet in nature, like that you are telling directly. Let us consider you are given with one unknown substance, right? You don't know what color it is absorbing. Let us consider this sponge, right? Initially, I don't know what color it is absorbing. When I don't know what color it is absorbing, then predicting what color it will emit is difficult one. Now already it is showing some color. Telling is quite easy, but when you go to some other substances, it becomes difficult to predict. So this is the pure experimental data given to us. Theoretically, one cannot predict it directly. Right? Theoretically, prediction becomes wrong. Right? All this is the experimental data. Only when we carry out the experiment, then only we can predict exactly what chemical shows what color. Now, to explain this color part, uh, we are given with one more theory in the chapter coordination compound called by the name crystal field theory. With the help of that theory, we can predict the color of the chemical also. That I will explain a little bit. We'll go in detail when we go to that chapter. Now, before that, you must understand one thing. When a given chemical is showing the color, right? In what situation a given chemical is showing color? Initially, I said you about these three things. See, when these three series elements are with either zero electrons in their d orbital or the orbital is completely filled, in such situation they are showing no color. It means the basic reason for the chemical to emit color, to show color, will be unpaired electron. Yes or no? In this situation, it is totally paired, and in this situation, there are no electrons. It means what possibility I am left with to say whether the given chemical will show some color or not is presence of unpaired electron in a d orbital. Sir, if I consider sodium in plus one state, you may ask me the question like this. Consider sodium in plus one oxidation state. It is with 10 electron which are revolving around its nucleus. Even sodium also has electron. Even the other chemicals are also having electrons. Then why sodium is colorless in the nature in plus one state or in its solid form when it is in plus one state? While the other chemicals are colored. The reason is splitting of d orbitals. In case of sodium, no splitting of orbitals takes place, but here particularly in case of d block elements, splitting of d orbitals takes place. It is because of which electronic transition takes place. See, when visible light falls on the chemical, when visible light falls on the chemical, the electrons present in this will absorb some amount of energy. When the electron present in this absorbs some amount of energy, definitely its energy will rise, it will get exact to the higher orbital. But in the higher orbital, it will not reset itself for a longer time. The time is around 10 to the power minus 7 or minus 6 something second. Right? Means the time lag is very, very small. Within that time duration, it will come back to its original orbital, to its original state. While coming back, it emits some amount of energy. That emitted energy is seen by our naked eyes. Means the light coming from the tube light falling on this substance, it is absorbing some energy and emitting some energy. That emitted light is falling in blue region. It is because of which it is looking blue in color. The substance can be anything. We can quote, we can apply this point to any substance. Suits perfectly, becomes no wrong. Right? Now, simply presence of unpaired electron is not enough to show color. Energy difference should come into existence. In these d block elements, when the given chemical is with unpaired electron, it is showing color. When it shows color, why it shows color, what happens when it is showing color? Let us see it here. Before that, let me drop all the 5 d orbitals. dxy, dyz, dzx, dx square minus y square, and dz square. dxy, dyz, dzx, dx square minus y square, and dz square. Here I am with 5 orbitals. Right. You see, once these 5 orbitals, yeah, you will come out with some similarity. Right? You can make 2 groups among these. See here, the first 3 orbitals, the lobes of the orbital is in between the axis. Right? The lobes of these 3 orbitals are in between the axis, and the lobes of these 2 orbitals are on the axis. Right? In coordination compound, there is one theory called by the name crystal field theory. In short, I will call it as CFT. Right? What happens? Let us consider in a ball, I have taken solution of some d block element. Right? Let us consider that chemical is with 1 electron in its 3d orbital. Let us consider. Right? Now, I am pouring some chemical. I am pouring some chemical to this ball where transition element is taken, where this chemical is with 1 electron in its d orbital. Some chemical is poured into it, to which I am calling as ligand, denoted by L. And ligand means what? It has a capacity to donate electrons to others, right? So this ligand is donating electron to this. Now, while donating electron, what crystal field theory says, the ligands will approach that metal atom or ion along the axis, right? This will attack on this along the axis. When this chemical attacks along the axis, now see, one point you must remember, that is the 5d orbitals. The 5d orbitals are degenerate in nature. Initially, when it is free from all these things, the d orbital is degenerate in nature. Degenerate in nature means the energy of all the 5 orbital is same. Right? When the energy of all the 5 orbital is same, means I can place this electron in any of the remaining 4 orbitals, because energy difference is no energy difference we find, energy is same, so it can place itself in any one of the orbital according to situation. Right? Now, when ligand attacks on this from the axis, when it attacks, what happens? See, ligand is with more electron density, and even this metal atom is also with electron in its d orbital. When the ligand is away from the metal atom, okay, no problem, the orbitals will be degenerate. Let us consider the ligand has come closer to the chemical, that particular D element. Now what happens? You all know well, the electronic repulsions comes into existence which are there between metal atom and the ligand. Ligand electron and metal electron will try to repel each other. When electron-electron repulsion takes place, you all know well, steric hindrance increases, because of which energy increases. Means energy of these orbitals increases. If I consider this as an energy axis, this is energy of this orbital, this will be the energy of this orbital, means energy has increased by this much unit. Okay, no problem. Now, after some time, this ligand has come very close to the metal atom, and which is coming along the axis. In that situation, what happens? This electron can be in any one of the orbital at any moment. Now, these two orbitals are coming along the axis, right? These are on the axis. When the ligand comes closer to these orbitals, if the electron is present in these two orbitals, then the repulsion between these two orbitals becomes more. Right? These two orbitals will repel, will try to go away from the ligand orbital. When it tries to go away from the ligand orbital, then generally, definitely its energy will increase. Energy of these two orbitals will increase. Then what I am left with? I am left with 3 more orbitals. Right? Here no repulsion takes place. Means the energy of this orbital will remain similar. It remains. It decreases a little bit. When it is increasing, means definitely its energy will decrease, right? So these 5 degenerate orbitals will split up into 2. Groups. The first group is with 2 orbitals called as EG group, and the second one is called as T2G group with 3 orbitals. This is with lower energy and this is with higher energy. Now, I said initially this element is with 1 electron in its d orbital. Consider it is with 1 electron in its T2G orbital. Right? The light is falling on it. Visible. Consider visible light has come and fall down it. Definitely this electron will absorb energy. When it absorbs energy, its energy increases. Right? When energy increases, we all know well, it will not reside itself here. Right? It will start to jump like a monkey from one tree to other tree. It will jump from one orbital to other orbital. Consider it went to this. Now, it will not stay here permanently. Within a fraction of second, that is around 10 to the power minus 7 to minus 8, it will get back to its original state. It will come back to its original state. While coming back, it emits some amount of energy. That emitted amount of energy, if it falls in visible region, then we can identify that color with our naked eyes. If the emitted energy is not falling in the visible region, then we cannot say that the given chemical is with some color. Right? This point means electron present in the given chemical absorbs energy, excites, comes back to its original state. While coming back, it emits energy that can be seen by our naked eyes if it is falling in visible region. This point can be applied to any other chemical. Right? Now, here, when this thing happens, see, I have explained all the process. In that process, I use the term ligand, which is electron-rich chemical, electron-rich species. If side by to this chemical, if there is such a ligand present which is approaching this chemical, if this thing happens, then only splitting will take place. If this splitting won't take place, means in the absence of ligand, no splitting takes place, and in that situation, that particular chemical won't show any color, it will be in colorless form. Right? Simply, I can say one thing on this color is, unless and until electronic transition takes place, chemical will not show color. This is what all about color of D block elements. Now, here I am with a few more examples belonging to coordination compounds. Let me write those. See, when this splitting takes place, right, I will be with two groups. In the empty orbitals, the electrons donated by the ligand will be placed. Now, simply in neutral or ionic form considering, I explained this. Let us consider a few examples of coordination compounds. Like, for example, hexaquatitanium plus 2 form, right? This chemical will show purple color. It is purple in nature, right? It shows purple color. It means it is absorbing some color. That absorbed color can be, it is showing purple. Purple means it will be somewhere here, right? Its complementary color is absorbed and this purple color is shown. Now, the next heading is formation of alloys. Now, alloy means what? When two different metal atoms are mixed, right? When I mix two different metal atoms or two different elements, which are with almost same radii, or the radii of difference should be within 15%. If it is the case, if I mix such two different elements, then the resulting compounds are called as alloys, right? For example, let us consider this is a zinc metal where atoms of zinc are arranged properly, right? Consider all these atoms belonging to zinc. Now, what I have done in this, I have mixed with some amount of copper. Right? Consider I replaced this atom by copper. Right? This means copper, this means zinc. Somewhere in between, I have mixed copper. Right? I am removing zinc atom, in place of it, I am placing copper. And by doing this, the new product that I get is called as alloys. For example, mixture of copper and zinc is called as brass. Mixture of copper and tin is called as bronze. Right? These alloys are more harder than the parent atom, more stronger than the parent atom, right? So this is all about the formation of alloys. Now next heading comes formation of interstitial compounds. Now what interstitial compound mean? It is quite simple one. Let us consider again. Consider one particular chemical, don't know what chemical it is, to which I am considering as X. This is a X chemical, right? You see the diagram properly. In between, you are having some small empty spaces. These are the small empty spaces present in this crystal, in this material, to which I will call as interstitial space, means the gap present in the crystal. Now, when I heat this chemical with the small atoms like hydrogen, carbon, nitrogen, right, boron, then these small atoms are trapped into these interstitial places. Consider carbon is trapped in it, right? On cooling, this material becomes a solid. When it becomes a solid, then the resulting compound is called as interstitial compounds. For example, consider all these bigger atoms belonging to iron. In between, some empty spaces are present. This iron is mixed with carbon, and I have heated it to the most extent. Then what happens? This carbon and iron mixes with each other properly. On cooling, I will get one solid bar, right? When I get solid bar, this carbon will be trapped in the interstitial sites, and that resulting compound can be called as steel. That you are familiar with it, right? Steel means what? Mixture of iron and carbon. Particular proportion of carbon when I mix with iron, then its stiffness will increase, right? Now, what will be the properties of interstitial compounds? What can be the properties, right? What can be the other examples? Other examples can be Mn4n, Fe3H, Ti3C, TiH1.7, VH0.56, etc., etc. These are a few other examples belonging to this interstitial compound. Now, what are the properties? See here. Initially, in the parent atom, there were so many empty spaces present. And after treating it with carbon, its empty space is filled by carbon, means density has increased. Density of interstitial compound is more than that of the parent atom. Electrical conductivity is retained as such. What it was previously, the same will be carried forward. Now, its melting point will increase, its strength will increase, and it is chemically inert. It will be chemically inert. So, this is what all about formation of interstitial compounds. Now, the next heading is catalytic property. Next thing is catalytic property. Now, before I go to it, let us consider what catalyst means, what is its function, for what it is used in industries. Let us consider I am carrying out one reaction. I don't know what reaction it is. In general, I am talking about this, right? reactant tends to product. Let us consider I am spending 100 rupees to complete this reaction, and this reaction is consuming around 10 hours to complete. Right? Now, let us consider I have used some X chemical in the same reaction in presence of this chemical. In presence of this chemical X, the same reaction is getting completed in 5 hours only with the expenditure of 50 rupees. See, you are finding almost double difference. Without catalyst, the same reaction is completed in 10 hours by the expenditure of 100 rupees. But in presence of catalyst, in presence of X, it is completed in 5 hours with the expenditure of 50 rupees only. Now, tell me which one is more fruitful. With X means in the presence of X, the reaction is more fruitful, it will give more profit, or in the absence of X? Definitely in the presence of X, right? So, this X in chemistry can be considered as catalyst. Now, you might have come to know what catalyst means. Catalyst is a substance, is a chemical which reduces cost of the reaction, and also time taken by the reaction. Right? It is because of which the industry people will get more profit. So in industry, it is because of this reason catalysts are used in the major extent. Right? Now, when a given chemical will act as a catalyst, this question is quite important. I am with a n number of substances around me, like this scale, this bottle, this pen, this kerchief, this table, floor, means marble, chalk, etc., etc., etc. Can I use all these substances as catalyst? No. There are some conditions. If that condition is followed by some particular chemical X, then that X can be considered as, can be called as catalyst. Now, what are those situations? What are those considerations? The first point is the given chemical should be with empty d orbitals. Second one, it should have large surface area. It should have large surface area. Then it should show variable oxidation state, and it should have intermediate complex forming tendency. Complex forming tendency. If a given substance follows these points, then that chemical will be going to act like a catalyst. Now, let us consider a few examples. The first example is decomposition of potassium chlorate, KClO3. This decomposes into KCl and O2. Right? The reaction is not balanced, on. Let us not bother about its balancing. Right? Simply let us focus how catalyst works on it. Right? When I simply heat this chemical, it will take some XYZ time. Right? When I mix it with NnO2, within some time it will decompose into KCl and O2. Let us consider one more example, that is hydrogen peroxide. Hydrogen peroxide, when it is exposed to sunlight, or simply when it is kept open, it will decompose to water and oxygen molecule, no doubt in that. But when I mix it with manganese dioxide, its decomposition process will be encouraged. Means the speed of the reaction, speed of decomposition will increase, and within fraction of time, that peroxide will decompose into water and oxygen molecule. In the same way, In the same way, when a mixture of iodine and bore sulfate is treated with ferric ion, means iron, then once again speed of a reaction can be enhanced. Now let us consider the reaction. 2I minus plus S2O8 minus 2 tends to 2SO4 minus 2 plus I2. This is the overall reaction. This reaction completes in two different steps. In the first step, two ferric ions combines with two iodide ions and converts into ferrous ion plus iodine molecule is evolved out in the form of gas. See, when iron is with plus 3 oxidation state, it is called as ferric, and when it is with plus 2, it is called as ferrous. Now, this ferrous ion once again take part in the reaction. This ferrous ion reacts with poor sulfate and converts this poor sulfate into sulfate ion plus, as usual, the initial chemical is regenerated. Initially I was with 2Fe plus 3 and at the end of the reaction once again I am with Fe plus 3. It means in the reaction the catalyst is not going to be consumed. It will be regenerated as it is at the end of the reaction. Here in this reaction, iron is acting as a catalyst. Now, in the same way, we are with so many number of catalysts, like for example, consider hydrogenation of unsaturated compounds or conversion of oil into ghee. Consider there what we do, we treat that oil with hydrogen gas in presence of nickel, palladium, or platinum, where these three chemicals are acting as a catalyst. Right, hydrogen is added to the unsaturation point, and that unsaturated double bonded triple bonded chemical will get converted into single bonded chemical, that is a saturated form of that chemical. Now consider manufacture of ammonia by Haber's process industrially. Right, in the manufacture of ammonia by Haber's process, iron and molybdenum is used as a catalyst. Iron and molybdenum is used as a catalyst. In the manufacture of sulfuric acid in contact process, manufacture of H2SO4 by contact process, vanadium pentoxide is used as a catalyst. Platinized asbestos is used as a catalyst in the manufacture of nitric acid. Right, like this, where with different chemicals according to situation we make use. This is what all about catalytic property. Now here what you have to remember is, when a given chemical can be considered as a catalyst, the given chemical should be with empty d orbitals. It should have large surface area, it should show variable oxidation state, it should have complex forming or intermediate complex forming tendency, and it should be regenerated as it is at the end of the reaction. If it is the case, if this is followed, then that particular chemical can be considered as a catalyst. Now here D block ends and starts F block. Now what F block mean, where it is placed in the periodic table? First, why this block is called as F block? The reason is the last coming electron enters in F orbital. Right? It is because of which it is called as F block. This F block is placed at the bottom of the periodic table. Right? This F block is placed at the bottom of the periodic table. This one is F block, which is placed at the bottom. It is with two series. The first series is called Lanthnoid series, and the second series is called Actinide series. The Lanthnoid series is with 14 elements. which starts from atomic number 58 and ends at 71. That is from cerium up to lutetium. Right. Now, even in actinide series, where 14 elements, right, and the series starts from actinium. Now, let us not bother about the actinide series. Today, let us discuss only lanthanide series. In lanthanide series, in total, we have 14 elements, and the series starts from lanthanum. Right? Total number of 14 elements are lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. See, here we are with these many elements. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. In total, I wrote 15 elements, but while explaining, I said we are with only 14 elements in lanthanide series. Right? Actually, the series starts from cerium and ends at lutetium with atomic number 71. Then why I wrote lanthanum here? The reason is this is the starting point of this series, right? Some of the properties are matching with this. It is because of which lanthanum is, while studying lanthanum is considered in the same series, right? After lanthanum, these elements are followed. So it is because of this reason, even this series is called as lanthanide series. The name came from lanthanum, lanthanide series. In general, it is denoted by Ln. Now, this lanthanide series is also called as rare earth elements. Rare earth elements. Now, you may have a doubt why these elements are called as rare earth elements. The reason is in the earth crust. In the earth crust, we get these elements in a rare amount. Means at one place we cannot get it in bulk. It is evenly spread throughout the earth crust. Wherever we get it, it will be in small amount. It will be in rare amount. It is because of that reason. Even this series is called as rare earth elements. Now, the general electronic configuration of this block is general electronic configuration is n minus 2 f 1 to 14, n minus 1 d 0 to 1, and ns 2. Now, let us try to write electronic configuration of few of the elements, that is lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium. Okay, let us write till here. Now first, lanthanum. Lanthanum atomic number is 57, right? 2, 10, 18, 36, 54. Helium, neon, argon, krypton, xenon. Atomic number of xenon is 54, right? 4f, 5d, 6s. Xenon 54, 55, 56, 57 with f orbital having 0 electrons. Now, cerium is with atomic number 58. The configuration will be xenon 4f1, 5d1, 6s2. Now, before I go to the next, you may ask me, sir, d orbital can accommodate maximum of 10 electrons. Right? Yes or no? D orbital is with 5 suborbitals. In each orbital, I can place 2 orbitals. So in total, I can place 10 electrons in the D orbital. But here I have placed only 1 electron, and after that, when I go to next, I am shifting the next electron into F orbital. Why it is so? The reason is when one electron is added to 5 orbital, fifth 5d orbital, suddenly energy of 4s decreases. Right? Suddenly energy of 4s orbital decreases, because of which the next coming electron takes entry into F orbital. So from here, F block starts not from lanthanum, because in lanthanum the last coming electron is entering into D orbital, not F. This you must understand, right? Okay. Now, Frmtin with atomic number 59. Xenon 4F 5D 6S. C. 2. Now, in this, I should add one more electron. So, how should I write? Should I write it as 4F to 5D1? No. This electron is again shifted to 4F orbital. Now, the next configuration will be 4F3 5D0 6S2. Now the same trend is continued. Neodymium 4F4 6S2. Next comes xenon 4F5 6S2. Xenon 4F6 6S2. Xenon 4F7 6S2. Now gadolinium. Alright, gadolinium atomic number is 64 with configuration xenon 4F7 5D1 6S2. As you all know well, exactly how the configurations are more stable. To attain more stability, the next coming electron takes entry. It means forcibly it is shifted into d orbital just to feel maximum stability. So see, up to here continuously electrons were added in f orbital. Suddenly at gadolinium, the entry of electron takes place in d orbital but not in f. Means this comes in exceptional case. It is because of this reason the electronic configuration of gadolinium is quite important. When question comes on electronic configuration either in JW or in NEET, the question will be asked on either chromium, copper, or gadolinium. If question comes on electronic configuration, question will be belonging to these three. No other question will come. If it comes, then the other two elements will be these two, europium and terbium. Right? Its configuration will be noble gas 4F7, 8, 9. Sorry, 6. Europium, no. Now terbium configuration will be noble gas 4F9, 5D0, 6S2. Right? Only question will come on this file. Its configuration will be noble gas 3D5, 4S1. This will be noble gas 3D10, 4S1, and its configuration is noble gas 4F7, 5D1, 6S2. Better remember this. So many times this question is been asked in the exam. Right? So this is what all about the electronic configuration of F block. Now the next heading is oxidation state. The common oxidation state of F block is +3. Right? Means where these lanthanide series elements feel stable themselves. Common oxidation state is +3. Right? All the elements present in this series will have this configuration. Right from what? Lanthanum up to lutetium. That is from atomic number 57 to what? 71. Now, except this, few of the elements will show some other configurations. For example, europium in +2 state, right? Terbium dysprosium shows E1 +4 oxidation state. Samarium shows E1 +4 oxidation state along with +3, or it will show E1 +2 oxidation state like europium, right? The last two elements, ytterbium and lutetium, will show +3 as well as +4 oxidation state. Now see here, europium is in +2 oxidation state. As I said, all the elements present in this block will feel more stable when they are in +3 oxidation state. It means if the situation comes, this europium can lose one electron and converts into +3 form, means it is going to act like a reducing agent. Right? Now, consider yttrium with +4 oxidation state. Right? When it is at +4 oxidation state, elements present in this series 1 to 10 +3 configuration, in such situation, it will accept one electron if there is someone to donate and converts into +3, means it is going to act like a oxidizing agent. Right? So this is what about the oxidation state of lanthanides. Now, we are left hardly with two definitions, that is lanthanide contraction and consequences of lanthanide contraction. So in tomorrow next coming class, the chapter will get complete and we require a little time to end up to put full stop to this chapter, and we'll see few of the question, what type of question can be asked in the exam and on what heading. Right? Let us see it in the next coming class. Thank you.